Okay, we got a question from the homework, and what was that?
It was number 39 part B.
Homework 39?
No, problem 39 on homework 2.
Okay, 39, and we're on homework number 2. And you know what that is asking us?
So homework 39 was just find the polar coordinates for the point of intersection of the graphs of r equals 1 plus sine theta and r equals 2 sine theta.
So in this one, I don't think I can show well on the video because I'm going to have to use the graphing calculator to do this.
We only need B.
What's that?
We only need B.
Oh, okay. And what was B?
B was, now sketch the two graphs and notice how, well, we have to sketch them anyways. Note that they have another common point whose polar coordinates do not satisfy both equations. Explain why this happens.
Okay. So we can graph these by hand, and then we can talk about what you're going to see. When you're going to have to do this one on your calculator.
Yeah.
And what you're going to want to do is on your calculator to graph them simultaneously, not one and then the other, because their paths are going to cross, but they aren't going to pass like at the same angle theta at the same time if you think of that as time. So the 1 plus sine theta, that's going to be a what we call a Lima sum. And so if we just, for this one, if we plot the values at what are called the quadrantal angles, so that is, we want to know what is the R at these places on the coordinate axes there. So at 0, sine of 0 is 0, we get R as 1, and so that's going to be this point here. At pi over 2, sine is 1, so R will be 2, and so at pi over 2, we're going to be up at 2. At pi, sine will be 0 again, so this will be 1 again, and that's going to put us there. And at 3 pi over 2, sine is going to be negative 1, so we're going to get 0. So we're going to get, oh, isn't that nice? It's a cardioid. Okay, so that's an upside down heart there, a cardioid that's known as. Now, the second one is going to be just a circle, I believe, right? So if we plug in 0, we're going to get 0. If we plug in pi over 2, sine is going to be 1, times 2 is 2. And I believe if you graph this on your calculator, this is going to be a circle. I think this lies inside of that. I don't think that's exactly right. Did you do it that way? So I think the only 2 points of intersection are here. Yeah. So we would say their paths cross in 2 places, but they, like if these are 2 particles moving, one is moving, along this path, the cardioid, at the same time that the pink one's moving along the circle, then they, this, let's see, this will be at the pole, at the origin, when theta is 0 and also at pi. But the cardioid will be at 0, it's going to be over here, so they're not going to hit each other if they're 2 particles. And this will be up here at pi over 2, and at pi over 2, so will that. So these 2 particles will hit each other at theta equals pi over 2. And even though their paths will cross there, they won't be at the same place at the same time. So if those were, 2 particles, they would not hit each other. They wouldn't collide with each other there because they're going to pass that point at different times. And that's what I think they're trying to get at there. Does that kind of make sense? Good one. Anything else? All right. Well, that lays on. So we're talking about polars, and now we're going to try to see a connection with complex numbers. So this is now 11.2, and this is going to be geometric representation of complex numbers. let's see what you think of this. I think this is kind of cool. We're way beyond what we did in our Algebra 2 and AP Prep days. The little bit we did with complex numbers there. So we are going to talk about graphing complex numbers. And so we call what we use here an Argonne diagram. And it's named after Jean Argonne. There's a whole bunch of really good French mathematicians. And so this was, I think, around 1806, I believe. He came up with this. So what his idea is to take our XY axis and instead think of that as the horizontal axis as being the real axis. Those are going to be real numbers. And the vertical axis, those are going to be imaginaries. So what we have is a real axis and we have an imaginary axis. So for example, if we have a complex number like, say, 2 plus 3i, then we would graph that by going 2 in the real direction on the horizontal and 3 on the vertical. And we can, at various times, think of that as a point, or we can flow and think of it as a vector. And so we'll kind of bounce back and forth between, or maybe instead of bouncing, flow between those as it suits our needs. So don't try not to get hung up with that. I know that can be a little confusing at first. So in this case, what we would say, these are the rectangular coordinates for that complex number. What we talked about last time, we can also do this with polars. And so we could think of not only, like in this case, we can think of this as being like the ordered pair 2, 3, where these are our rectangular coordinates. We're thinking of those as x and y's, but we can also think of those as polar coordinates, where we'd have an r and a theta. So using what we talked about last time, we know the connection between these, that if we know these rectangulars, we also know that x is going to be r cosine theta, and y is equal to r sine theta. You with me there? So in general, if we had some a plus bi, so any complex number written in rectangular form, we could replace the x part of that by r cosine theta plus, and the b part would be r sine theta, and then I'm going to put the I there. I'm going to put actually the I in front. Okay, so we have r cosine theta plus I times r sine theta. You with me there? So that's just going from a rectangular representation of that complex number to a polar representation of that same complex number. So now, mathematicians being, you can fill in the blank, efficient, lazy, they say, well, I get tired of writing this out all the time. So they first factor out the r and call that cosine theta. And the I is usually written in front, so you don't think, is that the sine of I? No, it's I times the sine of theta. And so what we see is that any complex number, any rectangular coordinates that we talked about last time, could be written as r and theta in polar form. So any complex number, 2 plus 3i, r a plus bi, can be written as r times cosine theta plus I sine theta for the right choice of r and theta that go with that ordered pair in rectangulars. You with me there? That's kind of a mind-blowing idea. So what mathematicians say, no, it's going to be always r times cosine theta plus I sine theta. So we abbreviate that and call it r cis cosine theta plus I sine theta, r cis theta. Crazy. That's what that represents. That's our polar representation for a complex number. So you know then that something like, say, and we'll use either degrees or radians. They're equally acceptable. So if we say 5 cis 60 degrees, that's a complex number written in polar form, and so you can convert that to its rectangular form by remembering that's going to be 5 cosine theta plus 5I sine theta. You with me there? And I don't need to read theta. We're going to call that 60 degrees because we know what the theta is. So that's going to be 5 cosine 60 degrees plus 5I sine 60 degrees. And fortunately, if our brains have not turned to jello over the summer, we know that the sine of 60 degrees is, oh, very good. And then we're going to get 5I times, that's not right. It should be a half, right? No, I was right the first time. No, cosine is a half. Sine is going to be, I'm the one whose brain turned to jello. Okay, and so then we can clean that up a little bit. So it's going to be an A plus BI form. So 5 halves plus 5 square root of 3 over 2I. So the idea is this polar representation, 5 cis 60 degrees, is the same thing as in rectangular form, the 5 halves plus 5 square root of 3 over 2I. Kind of crazy? Now, thinking back for a moment, you know, this representation in our Argonne diagram where we had the reals and the imaginaries. So we can talk about this length of this vector or arrow that takes us to that A plus BI or R cis theta, depending if we're going to be in rectangular or polar form for that complex number. Then that length right there, the length of that, I'm going to call it a vector, is called, and we have several different names for this. So these are all synonyms of each other. So these all mean the same thing. So we can call it the absolute value, or it's sometimes called, this is probably a new word for us, a modulus. We aren't going to use that one a lot, but it is used sometimes. So an absolute value or a modulus, or we will oftentimes, mostly with vectors, call it a magnitude. So absolute value, modulus, magnitude are all going to be the same. So if I say that z, I'm going to just name this. I don't want to use x or y because we've got that for other things sometimes. So that's our A plus BI, or if we call it R cis theta, then the absolute value of z, the absolute value of that complex number is going to be its length, which is going to be that square root of a squared plus b squared, which in the polar form is also known as, yeah, they're all modulus there, but so this square root of a squared plus b squared, where the a and b come from rectangular form, that's this length, which is that distance from the pole, which is what we've also called r. Right? So it's magnitude, or the absolute value, or that's the r in r cis theta. Okay, and the theta we call the polar angle. So you may see that referred to as the polar angle. Okay, so let's do an example of one of these. So let's say that we have, so let's express -3 plus 3i square root of -3 plus 3I square root of 3, I believe is what I have there, in polar form. Okay, so when we say that, we're talking about cis form. Does that make sense? Give you a moment. Anybody daring enough to do it at the board? I was afraid of that. Try not to take all the fun away, but I'm working through it here if you want to check, see what I'm doing. Want to go degrees or radians?
Radians.
Radians. So remembering that our original had a -3, so here's our Argonne diagram again. So -3 for the x and 3I squared of 3 for the imaginary part. The y part's going to put us in quadrant 3.
So would theta then be?
So the theta is going to be,
You have it as pi over 3.
I have the reference angle.
Oh, right.
So the actual theta is going to be 2 pi over 3. Is that okay? You okay with the r being 6? I think the theta is the hardest part. So then it's going to be then 6 cis 2 pi over 3. Now, generally speaking, the r should be positive. Not that it couldn't be understood if it was negative, but in general, when we write the r cis theta, the r should be positive. And the theta, you have a little bit more leniency there, but in general, we would try to make it be a positive angle between 0 and 2 pi or 0 and 360, although the negative angle is more acceptable than a negative r value. Okay. Because that is more like a length kind of thing. All right, let's go. You all right with this? So let's go the other direction. So I'm going to give you a polar form of complex number, and you can find it in rectangular form. So this time we will express 4 cis 210 degrees, we will say in rectangular form. And by rectangular form, I mean we want our answer to be a plus bi. Remember, the cis means cosine theta plus I sine theta. Anybody up to cosine 210 yet? Very nice. So we're in quadrant 3, so that's going to be a negative square root of 3 over 2. And sine 210, because we're in quadrant 3, is going to be negative. Does that look okay? Because everything's quadrant negative 3. And then you can cancel. So we get the 2 square root of 3, negative 2 square root of 3 minus 2i. Okay. So what we're going to do next, we all right with this? Colton, you okay? So where it gets cool, I mean, that's interesting enough in itself. But the real power in the polar representation is going to come when we do some arithmetic with it. In particular, we're going to look at multiplying complex numbers today. And then tomorrow, we'll talk about powers of complex numbers and roots of complex numbers, which would be, I don't know how you would do that in rectangular form, but it's pretty slick when you're in polar form. So let's multiply and divide. So we're going to multiply and divide complex numbers. You had to do a very little bit of this in AP Prep, and I imagine even in Algebra 2, but you don't have to do very much of it to get pretty tired of it, particularly the division part. So let's look at, say, we'll do this the old way first. So we're going to do the old brute force way of doing this. And then we're not really going to prove why it works the way it does, although we could, but we'll make an observation about how this would be so much easier to do if it was in polar form. So let's say that we have x is going to be, let's say, 4 cis pi over 3. And let's say y is going to be 6 cis pi over 6. So to do this the old way, what we're going to do is we'll convert these to rectangular form, a plus bi. Then we're going to take those and brute force multiply those out. And then once we get to there, then we'll talk together about how to go, because I maybe do it a little bit in a non-traditional way, about how to convert from the rectangular answer back to polar form. And then we're going to look at the polar version we started with and our answer and see if we can't make a hypothesis. Okay, so we're going to call that 4 cosine pi over 3 plus 4i sine pi over 3. And let's see, cosine, tell me if I'm going too fast. Cosine pi over 3 is what? 1/2. Plus 4i sine pi over 3 is square root of 3 over 2. And so the 2's cancel, so we get 2 plus the 2's cancel and get 2i square root of 3. So there is the rectangular version of our original 4 cis pi over 3 that we called x. Now we'll do the same thing and convert the y. So that's going to be 6 cosine pi over 6 plus 6i sine pi over 6. And the cosine of pi over 6 is 2, and sine of pi over 6 is a half. So we're left with 3 square root of 3 plus 3i. Does that look good? So now here comes the brute force slog. Yeah. So we're going to multiply the 2 plus 2i squared root of 3 times the 3 square root of 3 plus 3i. Okay? So the 2 times 3 square root of 3 is going to be 6 square root of 3. 2 times 3i is going to be 6i. Okay, here we go. 2i squared root of 3 times 3 squared root of 3. 2 times 3 is going to be 6. Square root of 3 times square root of 3, 3 times the 6 is 18i. Did I do that right? And then now you get crazy too. The 2 times 3 is going to be 6 squared root of 3. I times I is going to be I squared, which is negative 1. So that's going to be negative 6 square root of 3. Oh, can you believe it? Look at that. The 6 square root of 3's kill each other off. What a carefully constructed problem. It's going to be 18i. Okay? Have it your way. 6 plus 18, I'll concede, is 24i. Is that okay? Now, we're going to convert this. Now, this is in our polar form. Here's the way I think of it when it's a nice one like this, to convert it into rectangulars. I'm going to think of it visually on an Argonne diagram. So that 24i is going to be 0 on the real and 24 on the imaginary axis. So it's going to be like up here, 24 up on the imaginary axis and right on the axis. Okay, so now we're going to convert this into cis form. So the r is going to be 24, the distance from the pole, and the theta is going to be pi over 2. So the 24i, which is the rectangular representation of that complex number, in polar form is going to be 24 cis pi over 2. Okay? Now, we're going to squint at that thing. We're going to squint at this thing here, our answer, and also squint at where we started. Now let's see, what happened when we multiplied x times y? What about this 24? Product of those. So the r value here is the product of these r values there. Now think of this, pi over 3 is like 2/6 pi, right? We've got a common denominator. This would be 2/6. That's 1/6. When you add those, you get 3/6, which is pi over 2. Oh, can you believe it? So, do believe it. In general, our claim, which we are not going to prove, but we will accept to be true, because it is going to be that if x is, let's say x1 is r1 cis theta sub 1. You with me? And x sub 2, different now, maybe, complex number is r sub 2 cis theta sub 2. Then, if we multiply x1 times x2, we multiply two complex numbers in polar form, what we're going to get is what? R1 times R2 cis theta 1 plus theta 2. Oh, it just doesn't get much better than that. Okay, now since we're doing all this without proof anyway, let's roll with it. What would you guess, if you had to guess, about how we might divide two complex numbers in polar form? Well, see, when we multiply them, we multiply their R values. When we divide them, we're going to actually divide their R values. It's going to be R1 divided by R2 cis. Oh, you guys are good. You're going to subtract their angles. True story. Which we're not going to prove. It's not that hard, but you have to use the sum and difference angles of sine, cosine, which I don't want to get down and dirty in. Let's see, we did this before. What numbers did we have there? We had,
4 cis.
so x was 4 cis pi over 3, and we said y was 6 cis pi over 6. And we already did the multiplication. So should we do the division? Shall we, what do you want to do? X divided by y or y divided by x?
Yeah.
So you can do these nicer. Okay, I'm okay with that. Y divided by x. See what you got. Doesn't take long, does it? Isn't that crazy? So we're gonna go. So we got 4. I'll come back to that 6. Oh, why do I don't have it your way? And we picked this so that this would work out nice. There's a purpose to that. So we're going to take the R value of y divided by the R value of x. But now the penalty we pay is we're going to have to subtract here. So that simplifies to 3 halves. And this is 1/6 minus 2/6, so we get, and I'm okay with that. You know, I think that's perfectly well understood. Probably a better answer would be to write the negative pi over 6 as a positive angle. So this is equivalent to 3 halves cis 11 pi over 6. And I wouldn't count that wrong, but I think it might be a little better in that form there. Okay? Oh, I think we should be daring. How about if we do reciprocal of x, 1 divided by x. How might we do that? I'm open to suggestion here. Well, I mean, you might reason your way another way, but here's a way we can do this, I think, safely with what we already know. We know what x is in polar form. There it is. 1 is a complex number. It's in rectangular form now. Can we write 1 in polar form? Again, I would say, think Argonne diagram, right? And it's going to be 1, 0. It's going to be right here. Right? Okay, so now what we need from this is what's the R and what's the theta? 1 cis 0. Very nice. So we could think of this as being 1 cis 0. Right? That is 1 in polar form, cis form. And we already have the 4 cis pi over 3. And so we get 1/4 cis. Negative pi over 3 would be okay. We can maybe write it better. If we can improve on correct. Yeah.
On the AP test, will they let us do negative?
I don't think that's the level. This is not, sys form won't be on the AP.
Okay.
Now, we have left AP. We're on our walk, so we're wandering around. Okay, questions on that? Okay, so we're good to go for the assignment. I'm going to stop the video, but maybe we can see what else we can do here.